Hello everyone. I'm going to introduce my second word. It's called multilayer transformer. Gradient can be approximated in almost linear time. I would like to first introduce our two main results. The first result is about fast computation. We have theoretically proved that the gradient of a multilayer transformer can be calculated in almost linear time, which is n to the power of 1 plus small 1, which is a great improvement from the naive n squared time. Then I would also like to, the second result is the small approximation error. We have proved that the approximation error can be bounded by 1 over poly n, which is negligible compared to the speed up of the attention computation. Here we use n to denote the input sequence length, which is extremely large in long context scenarios used by modern large language models. Then I would like to provide the technical overview of our method. The high-level idea of our method is to use the low-rank nature of the attention matrix. We can see that the standard computation of the attention requires a n by d Q matrix and a d by n K transpose matrix. The multiplication of these two matrices will pass a row-wise softmax operation to get the orange color attention matrix. The softmax operation will eliminate the low-rank nature of the QK transpose matrix, but intuitively we think that this kind of nature maybe somehow can be used to approximate the orange matrix. The original bottleneck of the attention computation is between the attention matrix and the V matrix. The attention matrix is of size n by n, and the V matrix is of size n by d. So the multiplication of the attention matrix and the V matrix take up to n squared d time. Here we assume n is extremely long, so the n squared d time is equals to big O n squared time. Then we have proposed our method, which is displayed on the bottom row of this image. We use two low-rank matrices V1 to approximate the orange color attention matrix. We swap the multiplication sequence of the matrix. The first step, we calculated V1 transpose V, and this will take up to knd time. The second step, we will calculate the previous results with left multiplication of U1. This will take up to nkd time. K here is a small number which is equals to n to the power of small o1. By this way, we can accelerate the attention computation from n squared time to n to the 1 plus o1 time. Let's dive deeper into the technical details. First, we will review the softmax attention. So suppose we have a vector in the dimension of d, and we want to apply the softmax activation on this vector. The first step is we're calculating the exponential operation on each xi. The second step is calculating the summation. The third step is dividing each term by the summation. The low rank approximating here used actually focusing on the first step, the exponential step, to achieve the acceleration process. To calculate each item in the attention matrix is actually the exponential of the inner product of two vectors, one from Q and one from K. Let's say that we have a vector A in dimension D, which comes from the matrix Q, and a vector B in dimension D. This comes from in matrix K. Then we have to apply the exponential operation on the inner product of A and B, and then we can use the Taylor extension to approximate this result. We first extend the inner product to the summation form, and then we use the Taylor extension and we just approximate with enough terms here. Then we can transpose this summation and multiplication to inner product of two vector u and v. And here uv are in the dimension k. Then we can use this kind of uv to construct the matrix u1 and v1, which is by k, and then we can get our low-rank matrix. Let's get back to the technical overview. Actually, we have this attention matrix, and we can decompose it into a U1 and V1 by the aforementioned Taylor expansion method. Then we swap the multiplication sequence of the following three matrices. We can get the acceleration of the attention computation. By this way, we can apply all these terms to the backward propagation of the multilayer transformers. Then we can accelerate the entire process of the gradient backpropagation. That is my presentation for the multilayer transformers. Thank you for listening.